We are back to continue Chapter 3, Ionic Bonding and Simple Ionic Compounds. So the remainder of this chapter is looking at these compounds that we can form through ionic bonding, which we looked at in our last video. And so we're going to write out chemical formulas for ionic compounds, and we're going to name them. So let's start off with writing formulas. And so as we mentioned before, there are two types of ionic compounds that we can have. We can either have binary compounds or we can have compounds with polyatomic ions. But regardless of if we're dealing with binary, which remember means we have two elements, or if we're dealing with compounds that contain polyatomic ions, we're looking at the same method here, which is where we take our charges of each individual ion and we use that in order to determine how many of each atom or ion is needed in order for our compound to be neutral. So let's say, for instance, we're looking at magnesium and nitrogen. So magnesium, we look on our periodic table, we see that's a 2+ charge because it's in the second column. And nitrogen is going to be a 3- charge because of its location in the periodic table. So the easiest way to make sure that we're ending up with a neutral compound is just to take these charges and cross them over to become the subscripts. But we always take the absolute value because we're not going to have a -3 subscript. So the compound now becomes Mg3N2. So we need 3 magnesium ions and 2 nitrogen ions in order to make this compound. So let's try another one. Let's look at lithium and sulfur. So lithium has a +1 charge. Sulfur has a 2- charge. Again, we're just looking at the periodic table in order to figure those out. And so if we take those charges and cross them over, make them subscripts, now lithium is going to be Li2 and S is going to have a 1, and we don't actually write the 1. The 1 is assumed if there's not a subscript written. So it becomes Li2S. What about if we have two ions that have the same charge but opposite in sign? So for instance, what about calcium and oxygen? So calcium, we know, is a 2+ charge. Oxygen is a 2- charge. So we take these charges and ideally we would bring them down, and so we would think that our answer is Ca2O2. But for ionic compounds, you always want to reduce the subscripts as low as possible. So since both of these subscripts are 2 or are divisible by 2, this is actually not the correct formula. The correct formula would be CaO, because we only need one of each ion in order for our compound to completely be neutral. So let's try one more. Let's try one with a transition metal. So let's look at iron 2+ and fluorine. And so fluorine, we look at the periodic table and we can see that it's a -1. Take those charges. And so our final compound is going to be FeF2. So these are all binary compounds because they're made up of 2 different elements. So let's look at what happens when we have polyatomic ions. We're still going to look at the exact same method where we take our charges and we cross them and make them subscripts. So let's say, for instance, we're looking at sodium with nitrate. So sodium we know is Na+ from the periodic table. Nitrate is NO3 negative, and that's just one that you have to have memorized. So NaNO3, once we take our charges, they're both 1. And so remember, if the subscript is 1, we don't need to write it out. So it's just going to be NaNO3 as our final answer. What about if we had potassium, which we know is K+, and sulfate, which you have to memorize as SO4 2-. Take those charges, swap them, and we get K2SO4. But what if instead we need to have a subscript associated with the polyatomic ion? So what if instead we're looking at something like strontium, Sr, with hydroxide, OH negative. So here, our subscript for the OH is now going to become 2. So normally we would think that we would just want to write it as SrOH2, but if we write it like this, it looks like the 2 only belongs to the H, when the 2 belongs to the entirety of hydroxide. So when we're adding a new subscript to a polyatomic ion, we have to put the polyatomic ion in parentheses. So one more time, when we are adding a subscript to a polyatomic ion, we have to put that polyatomic ion in parentheses. So let's try one more with the parentheses method. Let's look at magnesium, which we know is 2+, and phosphate, PO4 3-. Take these charges, switch them. So we have Mg, we know our subscript is going to be 3. PO4, our new subscript is going to be 2, so we have to put it in parentheses so that the 2 belongs to both the P and the O. That 2 then gets distributed to both of them. Now it's possible for us to have 2 polyatomic ions put together because we have some polyatomics that are positive and some that are negative. So for instance, we could have something like ammonium, NH4+, and nitrate, NO3-. And so when we take those, it's 1 and 1. So when we put them together, we end up with NH4, NO3. So none of those need the parentheses because we're not adding any new subscripts there. So this is the case for ionic compounds. Remember, our goal is just to try and make these compounds neutral, which is why we're taking their charges and swapping them out. Now let's look at naming these compounds. So if we're to name compounds that are ionic and are binary, it's fairly straightforward. What we're going to do for binary compounds is name the metal, and then name the anion with "ide." So remember, we discussed that when you're naming an anion, its ending always changes to "ide." So we had a couple of examples that we just looked at. We had Mg3N2. So we name the metal. This is magnesium. And the anion is nitride. Right? The first syllable plus "ide." Then we looked at Li2S. So name the metal, lithium. Name the anion, sulfide. Then we had CaO. Name the metal, calcium. Name the anion, oxide. So this is what we do with binary compounds that do not include transition metals. We have separate rules for transition metals. If we're dealing with compounds with polyatomic ions, we name any other part of the compound as normal. Name any part that is not a polyatomic ion. And I'm going to abbreviate polyatomic ion as PAI. So name any part that is not a polyatomic ion as normal. And then the name of a polyatomic ion does not change. So we had, for instance, NaNO3. So sodium is not considered a polyatomic ion, so we name it as normal, which is sodium. And then nitrate, the name of the polyatomic ion does not change. So this is sodium nitrate. We had K2SO4. So this would be potassium. Name of sulfate doesn't change. We had a compound that contained 2 polyatomic ions. So that was NH4NO3. Since it's all polyatomic ions, none of their names change. So this is ammonium nitrate. And it's possible that our anion is not going to be the polyatomic ion. So we could have something like NH4Cl, where NH4 is the polyatomic ion, so that's named as ammonium. And then Cl is part that is not polyatomic, so it's named normally, which is chloride, right? Because it's an anion, and anions are named with "ide" at the end. So regardless of if you have parentheses or not, the name is not going to change here. So we do not have to specify how many of each element or how many of each ion we have in our compound. So just to make sure that this is hitting home, if we look at our example Mg3PO4 right, this contains a polyatomic ion. Magnesium stays the same. And then phosphate stays the same. So it doesn't matter here that we have parentheses. It's still named according to the same rules. So now let's see what happens if we throw in a transition metal. It doesn't matter if the transition metal is part of a binary compound or part of a polyatomic ion compound. The only difference here is that recall that transition metals need their charge written in Roman numerals. So the example that we had was FeF2. So we can't just say it's iron fluoride. We have to say that it's iron 2 fluoride. So this is an example of a binary compound including a transition metal. Let's look at one that includes a transition metal with a polyatomic ion. So for instance there, we could do, let's say Na is not a transition metal. Let's do CuSO4. So Cu is our metal, so we know that that's going to be copper. We'll have to fill in its charge, and then the polyatomic ion is sulfate. So how can we figure out what the charge of the copper is? Well, in the last slide, we saw that we took the charges and we crossed them. So now we can just do that backwards. If we were to take this out of the compound form, we know that this would become Cu with some charge, and this would become SO4 2-. Well, since neither of these have a new subscript, that means that they had to have the same magnitude of charge, but opposite in positive and negative. So copper had to have been a +2 in order to cancel out with the -2 of sulfate. So this is called copper 2 sulfate. So again, it doesn't matter if it's part of binary or if it's part of a polyatomic ion. We just need to write in that charge. Now there are some pieces of information that we need to be familiar with considering transition metals though, because we already know that transition metals are a little strange. They kind of have their own rules, and there are some more rules here that we have to look at. For instance, there are 2 transition metals that do not act as transition metals, and this is silver, Ag, and zinc, Zn. So transition metals are special because they have multiple charges, but silver is always going to be a +1, and zinc is always going to be a +2. So they are in the transition metal section of the periodic table, but they always have the same charge. Silver is always +1 and zinc is always +2. So you don't need to say silver 1 or zinc 2 when you're dealing with those compounds. We also have elements that are not transition metals but act as transition metals. And those are lead and tin. So if you look up lead and tin on the periodic table, you'll see that they are not part of the transition metal section, but they can have multiple different charges. They're in that column where we said that we switch our charges. And this is because these can either be +2 or +4. So for lead and tin, even though they're not in the transition metal section, we have to treat them as transition metals. And so for these two, for lead and tin, we have to use the Roman numerals to say what type of atom, what type of ion we're looking at. Whereas for silver and zinc, we do not need to use Roman numerals. So our last type of compound that has an ionic bond in it is called a hydrate. And this is simply an ionic compound that also contains water. And so the way that this is going to be written out is some ionic compound, and then there will be a dot, some number, so I'm just going to call it X, and then water, which is H2O. So when you're naming it, you name the ionic compound as you normally would. X is going to be some Greek prefix. And then when we're looking at H2O, we say hydrate. Whoa, I have no idea what that just happened. So what are the Greek prefixes? Well, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, 9 is nona, and 10 is deca. And we're not going to be going any higher than 10. And then just because I've run out of room, I'm going to take us to a blank screen. So let's say, for instance, we have this compound. So we can break this up into 3 different sections. So our first part is to name the ionic compound. So sodium is the metal, we just name that as normal. We have a polyatomic ion, so we don't change its name at all, so this is still sulfate. Then our next part, we have the 10. So going back to our list of Greek prefixes, 10 is deca. And then our last section is the water, and so we just say hydrate for water. So this is sodium sulfate decahydrate, and that's its full name. The very last piece of this chapter looks at what we call the formula weight of any kind of compound. And the formula weight is simply the mass of the compound using the masses of the periodic table. So a formula weight, by definition, is the sum of the atomic weights in a chemical formula. So this is how much the compound weighs, and this is going to be important for us later on this semester. So for instance, our first problem is find the formula weight of copper 2 sulfate pentahydrate. So I'm going to go to a new slide, or to a blank screen, so that we can work this out. So our compound was copper 2 sulfate pentahydrate. So copper we know is Cu. Copper 2 means it's a 2+ charge. Sulfate we know is SO4 2-. So when we take these and put them together, the 2 and the 2 cancel each other out. So we end up with CuSO4. Pent means 5. Hydrate is water. So there's our chemical formula. So using our periodic table, we can see based on the subscripts that for this compound, we have 1 copper atom, we have 1 sulfur atom, 4 oxygen atoms, and then for our water, we have this 5 as a coefficient which moves over to both. So we have 5 times 2, so that's 10 hydrogens, and 5 more oxygens. So we can go to our periodic table and we look up copper. So 1 times the mass of copper, which we go to our periodic table, and I have 63.546 AMU. For sulfur, we have 1 times its mass is 32.066 AMU. 4 times oxygen. Oxygen is one of those where it's so close that we can just round it and call it a day. So I'm going to say 4 times 16 since it's 0.999. Hydrogen, we have 10 times 1.008. And then oxygen again, 5 times 16. So we do that math. So this is 63.546. 1 times 32 is 32.066. 4 times 16 is 64. 10 times 1.008 is 10.08. And 5 times 16 is 80. And so then we add these all together. So 63.546 plus 32.066 plus 64 plus 10.08 plus 80. And the formula weight that I get is 249.692 AMU. Now, if you're using a different periodic table than me, your decimal places might be a little bit different, but you should still have at least 249.6. That should be the same. So then the next one that we had was find the formula weight of iron 3 nitrate. So we need to find the formula first so that we can find the weight. So iron 3 nitrate. So we have iron, we're told that it's 3 positive. Nitrate we know is NO3 negative. Swap those charges, and we have Fe NO3 3. So based on this formula, I have 1 iron. The 3 on the outside of the parentheses gets distributed. So I have 3 nitrogens, and 3 times 3 gives us 9 oxygens. So for iron, I have 1 times, look up iron on the periodic table, 55.845. 3 times nitrogen is 14.007. And 9 times oxygen, which we said we can just round up to 16. So that's 55.845. 3 times 14.007 gives us 42.021. And 9 times 16 gives us 144. Add these up together. 55.845 plus 42.021 plus 144, and we get 241.866 AMU. Again, your number might be a little bit different, but it should still be very close to 241.8. And that's the end of chapter 3.